Have you ever just, placed your phone down on one of those charging pads and you hear that little ding sound, see the battery light up, and there's absolutely no cable involved? It really does feel a bit like, well, like magic, doesn't it? Like tapping into some invisible power source. But obviously it's not actual magic. There's some really fascinating science hiding just beneath the surface there. So today on the deep dive, that's our mission. We want to pull back the curtain on this everyday convenience. We're diving into wireless charging and electromagnetic induction. We'll explore how it works, what it means for you day to day, and maybe even peek at what's coming next. Try to break it all down so it makes sense, even if, physics isn't your thing. And a guide for this exploration comes from Jen Byung-Chil's book, Jo-Yeon Cho. That translates roughly to True Beginner's First Steps in Electricity, published by Gilbert Publishing. Okay, let's unpack this. Let's start with what you probably notice immediately. The simple, everyday benefits. Think about your phone. The biggest win for wireless charging, hands down, has got to be the sheer simplicity, right?
No more fumbling with cables in the dark, trying to get the plug in the right way. Just place your phone down and bam, it connects. It starts charging. It's just clean. Now, okay, maybe it's not always quite as fast as some of those super speedy wired chargers these days, but for a lot of people, that convenience factor is totally worth it.
Oh, absolutely. That convenience is the hook, definitely. But the advantages go quite a bit deeper. Think about the device itself, its lifespan. With wired charging, you're plugging and unplugging constantly. Those ports, they wear out, they get loose, sometimes damaged. Wireless charging just bypasses that whole problem. There's no physical wear and tear on the port that can really help your device last longer. And another big thing, protection. Better protection. Without that open charging port, manufacturers can seal devices much more effectively against water and dust.
Ah, right. That makes sense. Less holes for stuff to get into.
Exactly. So if you accidentally drop your phone near water or use it somewhere dusty, having wireless charging capability contributes to making the whole device more robust, more durable. And then there's versatility. You often find pads that can charge your phone, your earbuds, maybe a smartwatch all at once.
Yeah, cuts down on the cable clutter.
Precisely, which is a big reason why it's become so common, almost standard, especially on newer phones. And while there are a couple of ways to do wireless power, you hear about electromagnetic induction and resonant induction, the one we use every day, the most common one. That's electromagnetic induction.
Okay, that's important. So for anyone listening who's thinking about getting a wireless charger or maybe just wants to make sure their current setup is good, there's something you mentioned. A standard, the key standard. Tell us about that. Why is that important?
Yes, key. It's spelled Q-E-I, pronounced qi, like the concept of energy flow in Chinese philosophy. It's the international standard set by a group called the Wireless Power Consortium, or WPC. Seeing that qi logo on a charger and on your device is basically your guarantee.
A guarantee of what exactly?
That they'll work together properly. Compatibility. Any key-certified device should work with any key-certified charger, regardless of the brand.
Got it. So look for the Qi mark. It's like the universal thumbs up for wireless charging. All right, so we know it's convenient, durable, makes devices tougher, and we should look for Qi. But the big question for a lot of us is still, how? How does putting a phone on a plastic pad make electricity jump across? Here's where it gets really interesting. Can you walk us through that invisible process?
I can certainly try. It's actually a really elegant application of a core physics principle, electromagnetic induction. It sounds complicated, but the basic idea is surprisingly straightforward. Essentially, a changing magnetic field can create or induce an electric current in a conductor nearby without touching it.
The changing magnetic field.
Yes, the changing part is key. And this isn't new tech, fundamentally. Michael Faraday figured this out way back in the 1800s. It's the same basic principle that lets huge power plants generate electricity. We've just miniaturized it incredibly cleverly for our gadgets. So let's break it down. Step 1 involves the charger itself. Inside that charging pad, there's a coil of wire. We call it the transmitting coil. Now, it's not just constantly blasting out a strong magnetic field. That would waste a ton of energy.
Right, that makes sense.
Instead, it usually sends out a very weak signal first. Think of it like a little hello, just checking if anything's there. Step 2, detection. When you place your phone, which has its own coil, the receiving coil onto the pad, the charger detects its presence. It gets that hello answered, basically.
Yeah.
Then, and only then, does the charger kick things up a notch. It starts generating a much stronger, changing electromagnetic field from its transmitting coil.
So it waits until the phone is actually there. Smart.
Exactly. Efficient. The key is that this field isn't static like a fridge magnet. It's oscillating, changing direction rapidly. Step 3, energy transfer. This oscillating magnetic field spreads out from the charger's coil, and it passes through the receiving coil inside your phone.
Okay, so the field reaches the phone's coil.
Precisely. And this interaction, this changing magnetic field moving across the wire in the phone's coil, is where the magic, the physics happens. Step 4. Electricity generation, that changing magnetic field interacting with the phone's coil. It pushes the electrons in the coil's wire, causing them to move. This movement of electrons is an electric current. It induces what's called an electromotive force, basically. It generates electricity right there inside the phone's coil.
Wow, so the field makes the electricity inside the phone.
You got it. It's like an invisible generator turning on. And finally, step 5, charging the battery. This freshly generated electric current is then managed by the phone's circuitry. It's converted into the right form and voltage, and then directed straight to your phone's battery to be stored. And voila, your phone charges. What's fascinating here is how elegantly this invisible dance between magnetic fields transfers real power.
Okay, wow, that's actually much clearer when you break it down like that. Not magic, definitely not, but incredibly clever. So it sounds pretty seamless, but are there any, gotchas, things we should be aware of to make sure it works well? I know sometimes my phone gets a bit warm, or maybe doesn't seem to charge if I don't place it just right.
Yes, those are very common observations, and they point to some important practical factors. First and foremost, distance matters a lot. Remember, the charger creates that electromagnetic field. The strength of that field drops off very quickly with distance. So for efficient power transfer, the receiving coil in your phone needs to be really close to the transmitting coil in the charger.
Which is why you have to put it right on the pad.
Exactly, and often aligned quite precisely. Misalignment is a common reason for slow charging or no charging at all. And trying to charge over, say, several inches or feet, that's a whole different challenge. You'd need an incredibly strong magnetic field from the charger. That leads to huge energy losses. Most of the power just radiates away as heat.
Okay, so that's inefficient.
Very, and potentially disruptive. A strong enough field could interfere with other nearby electronics. That's why we don't really have long-range wireless charging for phones yet. And about the warmth you mentioned. Some heat is normal during charging, wired or wireless. Energy transfer isn't perfectly efficient, but excessive heat can be a sign of poor alignment or sometimes an issue with the charger or the phone case. It's worth keeping an eye on. Too much heat isn't great for battery health long term. And this brings up another key practical warning: material interference.
Oh, like stuff getting in the way.
Exactly. That invisible magnetic field can be blocked or disrupted by certain materials. Think about metal. If you have, say, a thick metal plate in your phone case, maybe for a magnetic car mount or something?
Or even those pop socket things sometimes have metal bits, right?
Potentially, yes. Or just thick metal components in the case itself. If that metal gets between the charger coil and the phone coil, it can absorb or disrupt the changing magnetic field. The energy just doesn't transfer properly.
So it won't charge, or it'll charge really slowly.
Correct. You might get very poor charging or nothing at all. So a really important tip. If your wireless charging isn't working well, the first things to check are alignment and what kind of case or accessories you have on your phone. Take the case off and try charging. If it works then, the case is likely the culprit.
That's a great practical tip. Check the case. This raises an important question then. We see this technology in phones, earbuds, but it feels like such a fundamental principle, this electromagnetic induction. It's incredible to think it's behind so much. So what does this all mean for the future? Where else might we see this pop up?
That's a great point. It is fundamental. And now that wireless charging is so common, so integrated into how we think about powering devices, just placing it down, no thought required, that simplicity is driving innovation. We're definitely seeing active development to scale this up for bigger things.
Like what?
Well, the big one people talk about is electric vehicles, EVs. Imagine just parking your electric car in a designated spot in your garage, or even a public parking space, and it just starts charging automatically. No heavy cables to plug in, especially useful in bad weather.
Wow, okay, that would be a game changer.
It really would. The technology is being tested and developed right now. There are challenges, of course, efficiency over a slightly larger gap, handling much higher power levels, but the core principle is the same: electromagnetic induction. Beyond cars, think about maybe kitchen countertops that charge your blender or toaster just by placing them down, or office desks that power your laptop wirelessly, tools in a workshop, medical implants.
So cutting cords everywhere, essentially.
That seems to be the direction, if we connect this to the bigger picture. Electromagnetic induction offers this promise of truly seamless, invisible power delivery. It could fundamentally change how we design spaces and interact with technology.
So when you boil it all down, that super convenient wireless charging we use every day, it's not some kind of weird magic. It's this really clever, really elegant application of physics, electromagnetic induction. That simple act of placing your phone on the pad sets off this whole chain reaction of magnetic fields and induced currents, all invisible, all working to power up your device.
Exactly. And maybe a final thought to leave you with. As we move further into this hyper-connected world, just take a moment to consider how many other invisible forces, like this one, are quietly shaping the technology of tomorrow. Things that will make our lives maybe easier, more seamless, more integrated in ways we're probably only just starting to imagine. The potential for this kind of physics is really quite vast.
So the next time you drop your phone on that charging pad, maybe give a little nod to Michael Faraday and the clever engineers who shrunk his discovery down. Look for that chi mark, check your phone case, and appreciate the invisible dance of physics happening right there on your nightstand. It's a little piece of the future, right here in the present.